In just 1 month, NASA's Psyche spacecraft will launch on a journey to a metal-rich asteroid. Psyche will visit the unique asteroid, also called Psyche, orbiting the sun between Mars and Jupiter. I'm Raquel Villanueva, coming to you live from NASA's Jet Propulsion Laboratory in Southern California. Here at JPL, we manage the Psyche mission for NASA. JPL is also providing a technology experiment called Deep Space Optical Communications, or DSOC, that will fly with Psyche to test laser communications that could be used by future NASA missions. Today, members of the Psyche mission team will talk about why we're going to this asteroid and the final preparations taking place. We'll also be taking any questions you may have about Psyche. Joining us today are NASA Planetary Sciences Division Director Laurie Glaze, Psyche Principal Investigator Lindy Elkins-Tanton, Psyche Project Manager Henry Stone, DSOC Technologist Abi Biswas, Launch Services Program Mission Manager Serkan Bastug. For anyone watching who would like to submit a question, you can do so by using the Ask NASA hashtag. Our phone lines are now open to the media. You can ask a question by pressing *1. And to start, I would like to welcome JPL Director Laurie Leshin, who will provide some opening remarks.
Good morning or good afternoon, depending on where you are. The Psyche and DSOC teams have been very busy, focused on getting ready for launch, and 1 month out, we are in great shape. I could talk for hours about the cool science of this mission, but I won't, because you're going to hear about much more of that from our fantastic PI. But let me just say that Psyche is a mission of firsts. The first journey ever to a metal asteroid that could reveal clues about planetary cores and how planets form and evolve early in our solar system. The first ever deep space optical communications demo, high bandwidth optical communications, which have a potential to revolutionize future science and human spaceflight missions. First deep space use of Hall effect thrusters, and the first dedicated NASA launch on a SpaceX Falcon Heavy rocket, and the first interplanetary mission to be launched by a Falcon Heavy. It's going to be quite a show. We've brought our best minds together to make sure that Psyche and DSOC are successful. And as you all know, the journey hasn't always been easy. And that makes me even more proud of our incredible team here at JPL, at Maxar, at our university partners, including and especially at Arizona State, at MIT, and at the Technological University of Denmark, DTU. Also at APL, and countless other organizations, including our colleagues at Launch Services at Kennedy Space Center. It's a great example of how we dare mighty things together. In closing, we're excited, we're on track, and will continue to be vigilant heading into the last few weeks before the Psyche and DSOC launch. I'll hand it back to you, Raquel, by saying go Psyche, go DSOC.
Thank you so much, Laurie. And now I'm going to hand it over to our other Laurie, Laurie Glaze, who will tell us why NASA is so interested in asteroids.
Thank you, Raquel. So yeah, we're here today to talk about Psyche, and of course, Psyche, the Psyche asteroid is representative of one type of asteroid, but in fact, there are several types of asteroids, some with different chemical or physical properties, some that are found in distinct locations within the solar system, and each of those asteroids is a remnant of the earliest building blocks that made up all of the planets and moons. So by studying these small bodies, we can learn about the origin and evolution of our solar system, as well as the active processes that are still at work today. NASA has invested in multiple missions that are focused on these richly diverse populations of asteroids and the unique roles that each of those populations can play in telling the story of our solar system history. 3 of those missions are actually having big milestones this fall in what we're coming to call Asteroid Autumn, which is kind of cool, really fun. If I could have the first image, please. We're kicking off Asteroid Autumn, actually coming up at the end of September, with the return of samples from a mission called OSIRIS-REx. OSIRIS-REx launched in 2016. It visited an asteroid called Bennu, which is a near-Earth asteroid, and it collected a sample of the surface of that asteroid in October of 2020, and then has been journeying back to Earth since that time, and on September 24th is going to deliver that sample as it completes its journey, delivering the asteroid into the Utah desert on September 24th. Very excited about that. And then, of course, the OSIRIS-REx sample return is going to be quickly followed by the Psyche launch on October 5th, which we're going to hear a lot more about that here today. And then finally, on November 1st, the Lucy mission is going to fly by a main belt asteroid called Dinkinesh, where the team is going to try out the spacecraft's flyby operations in preparation for Lucy's visit that will begin in 2027, where they're visiting a group of asteroids called Trojans that lead and trail Jupiter in its orbit around the sun. The Psyche mission is part of NASA's Discovery program, which is an amazing program. I love this program. It has supported 16 planetary science missions to date. The Discovery program is kind of unique in planetary science in that it provides scientists and engineers opportunities to propose their imaginative, exciting, and focused planetary science missions. So I am so excited about this mission. You're going to hear from Lindy that this is truly a mission of discovery in the Discovery program. It is going to visit and see a metal-rich asteroid up close for the first time. I am so looking forward to seeing those first images. They are going to be spectacular when we finally get to see what this metal asteroid looks like up close. But before I hand things over to Lindy, I want to recognize that a mission like Psyche is only possible with the dedicated effort of hundreds of people. This mission had the additional complication of having to build and assemble hardware in the most difficult times of the pandemic. And I want to take this opportunity to thank Lindy, Henry, Matt Wallace, and the entire team for all your dedication and passion for this mission. So thank you, and take it away, Lindy.
Thank you so much, Laurie and Raquel. It's just such a treat to talk with you here today. So if you put up the first picture, please. Just a reminder, you know, we as humankind, we have visited either in person or robotically, we have visited bodies made of rock like Mercury and Venus and Mars and our moon, and bodies made of ice and gas like Jupiter and the outer giant planets. But what we have never seen before is a body with a largely metal surface, and that is what we think Psyche is. And so that is one of the things that makes it such important primary exploration and so exciting, because we don't know what we're going to see. Now, I'm saying we don't know what we're going to see right at the same time as I'm showing you this artist's impression. That's what it is. It's just an artist's impression. We worked so hard with this wonderful artist, Peter Rubin, to give him all of our science hypotheses so that he could draw this picture and bring to life what we imagine. Almost certainly not what we're going to see in the end, because space always surprises us. So we do have an idea of its shape. If we could switch to the next image. This is a shape model made by Mike Shepard and his team based on reflected radar and light off of the asteroid. And it gives us a sense of the shape of the body we're going to, but that's about the best that we have. And so just to remind us all what we actually have seen for Psyche, I'll show you the next image. This is Psyche in a backyard telescope. It's not much bigger in the Mount Wilson 60-inch, and even in Hubble, it's just a couple of pixels. So to remind you all that this is going to be primary exploration, we really don't know what we're going to see. Now, we've been working on this project since 2011, and this is a good opportunity for me to also thank the team. We've had over 2,000 people work on this project, and it is amazing what people can get done with the kind of dedication that we've had with this team. I'm so grateful to work with everyone who's been working on this team. So we're going to learn about, when we get to Psyche, a previously unstudied ingredient that went into making our habitable Earth, and that is the metal that is now in the Earth's core and the cores of all of the rocky planets, cores that we can never visit, but cores that we want to learn about. And Psyche is the singular largest metallic object in our solar system. And so if we want to learn about our cores, that's where we need to go. Psyche is not ever going to make us rich, even though it's made of metal. It's very, very far away. Even at its closest, it's 3 times farther away from the Earth than Mars is at its closest. So we are never bringing Psyche home. Psyche, we're going to learn about science, and we're going to learn about what a metal surface looks like and get ready for the next phases of our exploration. So we are pretty confident that Psyche is largely made of metal and partly has a metal surface because of its density. It's a very dense asteroid, currently the densest known asteroid, and because of the way that light and radar reflect off it. And we compare that reflected light spectrum to meteorites that have fallen to Earth, and that helps us know that it's largely made of metal. If you're wondering why we can be confident about that when really all we have seen of it is a speck of light. And so how do you prepare to study an unknown object? First of all, we're bringing imagers. We've got to know what it looks like. We've got to bring our cameras. And the imagers are built by Malin Space Science Systems and managed here at Arizona State University. We're going to bring magnetometers because we hope that it has the history of a magnetic field to teach us about when it was a core. And those magnetometers are built by Danish Technical University in Copenhagen. And then we're going to bring an amazing instrument called a gamma ray and neutron spectrometer built by Applied Physics Laboratory, which will allow us to measure the surface composition of the asteroid while in orbit. Because again, this isn't a lander, it's not a sample return, we're orbiting for 26 months. And finally, we'll do gravity science led out of MIT to discover more about the internal composition and structure of the body. And for that, we use the Doppler effect of our radar communications with our spacecraft. Now, we are still working so hard to get to launch. The team is full on it. We are beginning to feel that excitement of what is ahead, and we're confident that it's going to be a thrilling day on October 5th at the beginning of our launch period. So let me now pass it over to Henry Stone, who is our project manager at Jet Propulsion Laboratory.
All righty, thank you, Lindy. I am equally excited to get to talk with you today. I'd like to give you a little sense of what the spacecraft looks like, how it operates, and then give you some of the brief highlights on the mission profile. So if we could get the first slide up, please. So this is what the spacecraft will look like in its flight configuration, okay, after the solar arrays have been deployed, and it's on its journey to Psyche and how it will be flown when it's orbiting about the asteroid. Of course, the human is just there for scale. The human is not going on this mission. This is a purely robotic mission. But it does give you a size of the body of the spacecraft and the arrays. The spacecraft, you can see, is clearly dominated by these very large 5-panel solar arrays. The arrays together have about 800 square feet of solar collecting surface. And you may be wondering, well, those are awfully large. What do you need that? Well, this particular spacecraft, unlike many that go to deep space, which use chemical propulsion, uses solar electric propulsion. And we're leveraging that from the capabilities of our commercial partner, Maxar, up in Palo Alto, who designs and flies communication satellites that use this technology with these Hall thrusters. Anyway, the way that works is we collect all this electrical energy, and we use it to ionize xenon gas down into these elemental little particle ions. And then we accelerate those particles to extremely high speeds by passing them through a very strong electromagnetic field, which is part of the thruster itself. And then we eject those out the thruster, basically the thruster nozzle. And that allows us to generate the thrust that we will need to power this vehicle to its journey, 2.2 billion mile journey to get ourselves to the Psyche asteroid. The interesting thing about that is, unlike a chemical propulsion, is the thrust. At any one point in time, the thrust produced by these engines is an equivalent to having 2 little AA batteries sitting in the palm of your hand. Just the weight of that is all that's produced at any one point in time. But unlike the chemical mission, these thrusters are basically going to be on 24/7 the entire time. We've got a 5.5-year cruise and 2 years of operation around Psyche. And with those engines operating that continuous amount of time, we will pick up tremendous amounts, tens and thousands of miles per hour speed in order to reach our destination. So if I could have the next slide. This is another image. Again, the human there only for scale to give you a little bit of the sense of the size of the body of the spacecraft, where all the equipment is housed, all the sensors and instrumentation and the propulsion system. It's about 10 feet tall, 8 feet square on the bottom. Up on the top, you can see a key feature is the big round disc. That's our high gain antenna to communicate with Earth. There is a jungle gym, so to say, of trusses that kind of sit behind that, to which we've affixed our gamma ray neutron spectrometer, our magnetometer. The imagers on the right-hand image, you see kind of halfway up in the green flat area there, two little tubes sticking out. Those are our imagers. The other very large feature that sticks out the side of the body on the left-hand side there is the DSOC instrument that Raquel mentioned earlier, and AB in a few minutes will give you a few highlights on that particular instrument. This is obviously with the solar panels all folded up. This is the launch configuration. This is what it will look like when we attach it to the Falcon Heavy rocket for launch. And it's immediately after deployment and separation from the launch vehicle that the arrays will be deployed. So if we can go to the next picture, I just want to show you a real picture of what the spacecraft looks like in one of our high bays. And here you can see the solar arrays packed on the side, the imagers sticking out, and then on the top, that truss work is all covered with thermal blanketing. So that's the vehicle. It's fully fueled. It's ready to go. It's ready to be interfaced to the launch vehicle. So let me give you just a quick highlight of the mission profile. You can probably go to the next slide on that one as well, please. That's just another picture at another angle. So we're getting ready to launch here on October 5th, and we're all very excited about that. Immediately after launch, the vehicle is going to spend about 100 days in an initial checkout. This is where we will be turning on all the various pieces of equipment, make sure everything is operating and functioning properly and tuned in and dialed and ready to go. As soon as we've completed that initial checkout, we're going to fire up those Hall effect thrusters, and we're going to be on our way to Psyche. About 2.5 years from launch, we are going to do a Mars flyby. We're basically going to get a gravity assist and do a slingshot to further increase our velocity in order to spiral our way out to the Psyche asteroid, which is in the main asteroid belt, as mentioned, between Mars and Jupiter. So we have a long way to go. About 5.5 years from now, we'll be getting close to the end of the cruise period. And about June of 2029, our imagers will actually start to be able to take pictures of Psyche, which are no longer just a little dot. We'll actually start to see the body getting bigger and bigger, and we'll use those images to optically navigate our way in right to Psyche. So in about August of 2029 is the point at which we will drop into our first orbit. So we're going to orbit Psyche multiple times at 4 different altitudes. The first altitude is about 440 miles off of the surface, got a nice safe distance, and we'll do that for 2 months. It'll allow us to collect the necessary information for us to understand and model the shape and the strength of the gravitational field of this body. We don't know what that is right now. We haven't been there. But that's very important to allow us to safely navigate to lower and lower altitudes so that we can take higher and higher resolution measurements and images with all of our instrumentation in order to collect the scientific data that's necessary to accomplish the mission. So there are 4 different altitudes. At the lowest altitude, we're going to be down to a mere 40 miles off the surface of Psyche. Get some spectacular pictures, spectacular data. We will be doing that orbiting for about 26 months. So by the time we roll around at the end of that, it will be into about November of 2031, and that will come to the basically end of our prime mission. So that's a quick rundown of the mission profile. I'll just say in closing, it's, as Lindy mentioned, there's thousands of people that are involved to do a huge endeavor like this. And it's been a real pleasure and an honor for me to be able to lead that team here at the Jet Propulsion Laboratory. And I just very proud and really looking forward to the launch, and want to thank everybody on the team for the great work that they've done. With that, I will turn it over to Abi to give you a rundown of this great technology demo that we're flying as well.
Thank you, Henry, and hello, everybody. So the Psyche mission is hosting a ride-along experiment which will allow us to test the ability to return high-rate data from planetary distances. We're doing this by using a laser beam, which is orders of magnitude higher in frequency than state-of-the-art telecommunication radios. And with the high frequency comes the ability to serve as a carrier for high data rates. So at JPL, the Deep Space Optical Communications Project has developed and implemented this system, which is going to allow us to do NASA's first optical comm demonstration from distances farther than the moon. In fact, almost 1,000 times farther than the moon. Now, this huge increase in distance, because the last NASA demonstration was from the moon, this huge increase in distance brings with it new challenges and difficulties. And the DSOC project has developed technologies to overcome these challenges and to demonstrate a 10 times augmentation of traditional telecom data rates that we get from Mars today, let's say. And so if I can have the next slide, please. So here you can see a graphic of the DSOC payload that's integrated to the Psyche spacecraft. It's all covered up, of course, but that cylinder that you see with the gold cover, that's the sunshade that's connected to the payload. And when the aperture cover is deployed, laser light can enter and exit through that sunshade. So once Psyche launches, the DSOC technology demonstration starts almost day 16 after launch, and it'll operate at a weekly cadence. The first few weeks we'll do some commissioning and checkout, and then after that it'll operate at a weekly cadence for almost 2 years into the cruise of Psyche, ending in about September of 2025. And when the spacecraft high-gain antenna that you see there points to the deep space network, that's when we also can point our laser to the ground. If I may have the next chart, please. So inside that covered up payload picture sits this, what we call the flight laser transceiver. This is basically an off-axis telescope with a 22 centimeter mirror that is specially designed to both receive and transmit laser beams. And using this this is the key technology that allows us to do optical communications, and built within it are a host of new technologies, many of them which are flying in space for the first time. So the pointing of laser beams is very difficult, and that's one of the main challenges we're trying to overcome. And of course, there's a whole system built around achieving this. In addition to what I showed with the flight transceiver, there's also a significant ground element, and that ground and space element play sort of cooperatively to enable pointing. So if I may have the next chart, please. So so you can see we start the link by pointing a laser from the transmitter at Table Mountain, and then that laser beam is acquired by the spacecraft and used as a pointing reference to send the downlink laser beam back to the Palomar Observatory, the historical 5-meter Hale telescope. Just to give you an analogy of how difficult the laser beam pointing is, it's like aiming at a dime from about a mile away. And that's why we need this assistance from the ground laser beam, which gives us a stable point of reference to point back to the ground. So everything, all the testing and effort has gone into, we're prepared for launch, and we're very excited about launch and looking forward to the important lessons learned, which will in the future enable human missions to Mars and the use of very high resolution instruments. And with that, I'd like to hand this over to Serkan Bastug, who will tell us about the launch vehicle. Thank you.
Hey, thank you, Abi, and hello, everyone. I am the Psyche Launch Vehicle Mission Manager for the NASA Launch Services Program here at Kennedy Space Center. The NASA Launch Services Program is responsible for the acquisition and integration of the Falcon Heavy launch vehicle to the Psyche spacecraft. As already mentioned, this will be the first launch of the Falcon Heavy vehicle configuration by NASA, the first interplanetary mission for the Falcon Heavy, and the 8th Falcon Heavy overall. If we bring up my first image, here's a image of the Falcon Heavy can be seen here. This is the United Space Force 67 mission that was launched earlier this year. We'll be launching out of the historic Launch Complex 39A at Kennedy Space Center. This launch pad was originally built for the Saturn V program in the early 60s. Was built for the Saturn V program in the early 60s and also has a very long and rich history with the shuttle program. It is now being leased by SpaceX for their Falcon 9 full thrust and Falcon Heavy fleet of launch vehicles. All the launch vehicle primary hardware is currently at Kennedy Space Center getting ready for flight. For the Psyche mission, this will be the first flight of this vehicle's center core and the 4th flight for the reused side boosters. Integrated operations will begin within the next couple of weeks. This is where they begin the process of mating the Psyche spacecraft to the launch vehicle and encapsulating the spacecraft inside the 5-meter fairing. And if you can pull up my next image, this is an example of the SWAP mission being integrated into the encapsulated inside of the 5-meter fairing. As a part of the preparation for flight, the vehicle will undergo a static fire test on the pad a week before. This is to ensure the engines and flight systems are all working as expected. Once static fire is successfully completed, the encapsulated assembly with the Psyche spacecraft will be transported to the pad and mated to the launch vehicle. The launch opportunity window for Psyche is 21 consecutive days with 1 instantaneous launch window each day beginning on October 5th. So if we quickly go through the major flight events, if everything remains on schedule, on October 5th at 10:38 Eastern, we will have liftoff of the Psyche Falcon Heavy with the ignition of the 27 M1D engines providing just over 5 million pounds of thrust. At a little bit past 2 minutes, the side boosters will separate and begin their descent to landing zone 1 and landing zone 2 at Cape Canaveral Space Force Station. The next video has an image of the 2 side boosters landing. This is from the first heavy launch, the Falcon Heavy demo mission. We'll have center core booster separation at approximately 4 minutes. And then there'll be 2 burns of the M-BAC-D second stage with a coast in between the burns. Spacecraft separation deployment will occur at 62 minutes after liftoff, and the Psyche spacecraft will be on its way to its namesake destination. Everyone here at the NASA Launch Services Program at Kennedy Space Center is very excited to be a part of this incredible scientific mission. Not only will this be the first Falcon Heavy launch for NASA, but it will also be my first as a launch vehicle mission manager. So I feel especially fortunate to be a member of this team and participate in this unique and historic launch. Thank you very much for having me here today. Back over to you, Raquel.
Thank you so much, Serkan, and thank you to all our speakers today. We are now ready to take media questions. Remember to press *1 to get put in the queue, and please direct your questions to one of the panelists. We are also taking questions today through the hashtag #AskNASA. So to start, we have Bill Harwood from CBS News on the line.
Hey, thank you very much. This is a quick question for Lindy. Could you talk a little bit more about the range of possibilities in terms of what you'll see when you get there? And I realize you don't know, you've told us that, but when you say a metal-rich asteroid, what does that mean in terms of, bare deposits of metallic compounds? Do you expect some sort of soil blanketing some of these deposits, boulders, pebbles? I mean, maybe just give us a sense of the range of possibilities. Thanks.
I could not have a more fun question to be asked, and I will try to make this brief. So what do we know? We know from radar and from thermal measurements, the scientists who've been analyzing that think that the most consistent surface material with their data is very fine-grained metal. And so we've been asking ourselves, can you make fine-grained metal? Just like on the moon and Venus and Mars and so forth, you have a dust on the surface that's due to weathering, but there's no weathering on Psyche other than the solar wind. So far, experiments show the solar wind does not break up metal into little grains, but micrometeorite impacts do. And so one possibility is that the metal surface of Psyche is covered by tiny spiky cup-shaped micrometeorite impacts into metal and little tiny grains of metal that flew off of them when they happened, there's a wild possibility. Probably everything I tell you today is going to be wrong. We expect part of the surface to be metal and part of it not to be metal. What's the not metal part? Rock, sulfur, don't really know. I would say that the only thing we're pretty darn confident of is that there's metal there, and the metal is going to be similar to metal meteorites that fall to Earth, that is mostly iron. So if I were to stake my scientific reputation on that, those are the only really pretty firm bits of information that we have.
Great, thank you, Lindy. Now up next on the line is Jeff Faust from Space News.
Pardon me. Couple of questions for Laurie Glaze. One, can you provide the updated cost of the Psyche mission now that you've gotten through the issues that caused the launch delay from last year? And two, if there is a government shutdown on October 1st, if there's a lapse in funding, would the Psyche launch go forward on October 5th? Thanks.
Hi, Jeff, and thanks for the question. And I'm going to tell you, I'll be honest, I don't have the final cost number right at my fingertips, but we can get that for you, I'm sure, in real time here. The second question has to do with the potentiality of a government shutdown. You know, I'm here at NASA. It's not my spot. It's not my role to speculate on whether there will be a government shutdown and what the operating status is going to be. But we are, of course, monitoring that very, very closely. In the past, NASA has been prepared to request a waiver for operations, essential mission, and launch personnel to ensure that missions can meet their launch period. And we are certainly prepared to follow that same path here for Psyche to make sure we get off the ground.
Great, thank you, Laurie. And also on the line is Ramin Skiba with Wired Magazine.
Hi, thank you. This is a question for Laurie Glaze. I was wondering more about the long-term perspective here for NASA. You know, we already have the Moon to Mars program. Is our asteroids the next step? Is it going to be like Moon to Mars to asteroids, where in the future, you know, we actually will try to, you know, extract resources from asteroids, for example?
It's an interesting question, and certainly something that might be considered in the future. Right now, our focus is on Moon to Mars. And right now, for the NASA perspective, the asteroids are for scientific study. We also, of course, have a big program in planetary defense and trying to make sure that if there was any hazardous asteroids, but right now we're not focused on potential mining. I did get an answer for Jeff Faust's question. So while I have the microphone, let me just indicate that the investment up to this point in Psyche is approximately $1.2 billion. So there's that number.
Perfect, thank you so much. And we now have some social media questions coming in with the hashtag AskNASA. Prasad on YouTube asks, why was the Psyche asteroid in particular selected for such a mission? Lindy, would you like to take that one?
Yeah, our original science question was, how did metal cores and rocky exteriors form in the very earliest little planetesimals, baby planets in our solar system that went on to add up to become the Earth and our other rocky planets? These are things that if the solar system was a 24-hour day, they formed in the first 30 seconds. And so then we searched, where in our solar system can we go find out about this? And we settled on Psyche. There are about 9 known asteroids that seem to be made of metal. And Psyche is by far the largest and the one that is, I would say, roundish. And so that's why we chose Psyche.
Great, thank you, Lindy. And we also have another social media question coming in. Levitated Pit on YouTube asks, what kind of ground penetrating radar are you going to use as it is so metal rich? Henry, would you like to take that one?
We actually don't have ground penetrating radar on this particular mission. We'll be using a gamma ray neutron spectrometer to look at the elemental composition and the various metallic constituents. We'll be using our 2 imagers, which have equipped with filters that allow us to differentiate between different types of mineralogy and of course get the whole topology and the shape of the surface, but it helps in the mineralogical composition of the surface and the magnetic field. The magnetic field is particularly important, I think, to some of the hypotheses whereby if it was once a molten core of an early planetesimal or whatever, and then froze, it will have stored that magnetic field that was going on at that period of time into the rock or the other material, and we'll be able to detect that with our magnetometer. So it's really those three scientific instruments combined with the gravitational properties of the body, which we get from our telecom system, that will allow us to make the inferences about what Psyche actually is and its origins. And I think I could pass it over to Lindy to talk even more about that.
Yeah, I think possibly I used the word radar when I was talking about looking at Psyche using radar dishes on the Earth. And so that's how we've looked at Psyche and radar. Rest in peace, Arecibo bounced radar off of the asteroid Psyche, and we received the returns. And so maybe that's where radar came into the conversation.
Well, thank you both for the clarification on that question. And we're going back to the phone lines now with Marcia Smith with spacepolicyonline.com.
Thanks so much. So this is to Lindy and Henry. Your Psyche milestones go only as far as 2031. So could you talk about what you have in mind for an extended mission? And what happens at the very end? I mean, are you going to crash it into Psyche, or what's going to happen?
Yeah, I'll just say briefly, at the moment, this is just pie in the sky dreams, because we've got to reach mission success for our primary mission before NASA even considers what we might propose for an extended mission. But I will tell you, in my, PI's heart, what I'm hoping is that in the end we might get to orbit down closer and closer and closer to the surface, getting better and better data, and then we would in fact crash on the surface. But that is just my personal dream. There's nothing that's actually planned yet. And so, Henry, what would you add?
Well, yeah, that's kind of my dream as well. We have a great track record here at NASA that when we get our missions up and running, they tend to last a long time. We do a pretty good job at that, as evidenced by the rovers on Mars. And so if that comes to be, and there is NASA wants us to allow us to continue, I think we would propose to drop down to lower and lower altitudes, get higher resolution images, and just better data all around. It'd be very, very exciting.
Great, thank you both. We now have Will Robinson-Smith with Space Flight Now.
Yes, hi, thank you for taking the time to speak with us today. A question for either Henry or Lindy or both. In the process of approaching Psyche, and once you get it within optical view, did you learn anything, or have you learned anything from the DART teams about that final approach, that they were able to offer some words of wisdom or some guidance as you are guiding towards Psyche and making that final approach? Thanks.
Yeah, go Henry.
Yeah, I think, well, this mission actually is very similar to the Dawn that went to Ceres and Vesta and used this very technique. So we're quite familiar already with optically navigating in to bodies like this. So I think, we've had folks on our team who have had some interactions, I believe, with the DART team, but that particular aspect of our approach has kind of been paved already. So I think we're pretty confident that we know how to go about and do that.
And we have some more calls on the line. We have Steve Gorman with Reuters.
Yeah, hi. Thanks for taking the call. So I know you guys are primarily interested in the science of this asteroid and what it means in terms of revealing new insights into the formation of our planets and moons in the solar system. But because it is a rare metal-rich asteroid, there's been a lot of attention focused on what might be the value of the various kinds of metals that are in it. And I think it was Forbes magazine, I believe it was last year, or last couple of years, wrote an article where they said that if this thing, Psyche, could contain a core of iron, nickel, and gold worth $10 quadrillion. And I was wondering if you could tell us, like, do you have any idea where that came from, whether that's, actually there's any basis for that scientifically, or and also how rare is it, do you believe, these kinds of asteroids are in our solar system?
Can I take a first stab at that, and then I don't know, Laurie, is anybody else? This is really, I will just say it's my fault because I did do that calculation. It makes such a great headline, and there have been dozens or hundreds of headlines like that around the world, but it's false in every way. We have zero technology as a species to bring Psyche back to Earth. And if we did, it would likely be a catastrophic mistake, could we say? But say we were able to actually bring Psyche back, then it would flood the metals market and it would literally be worth nothing. And so calculating the value of it is, it's a fun intellectual exercise with no truth to it. We are not going there to mine an asteroid. NASA does not mine asteroids. There are other metal objects in the solar system for humans to think about in the future, but that's not our mission.
Great. Thank you, Lindy. And we also have another call on the line, Emily Lakdawala with Sky and Telescope.
Hi. First of all, thank you, Laurie, for wearing your NASA Pride pin. But this question is for Lindy. 6 years is a long time to wait for first light for your instruments. So what are your plans for cruise science? Do you have any departure science plans, Mars flyby science? And when does your approach science actually start?
Yeah, it is a long time, but we've got plenty of science planning to do. The big thing we're going to be doing the first 2 years is DSOC. That is going to be so exciting, and so we're focused on that. There's really no science in cruise, it's just calibrations. And then as soon as we're able to do any science with our approach photos, we'll start doing that. I want to add that we've already written the pipeline such that our photos will be put on the internet for everyone in the world to see within 30 minutes of our receipt. So we'll all get to do our science together as we approach the asteroid.
Great, thank you, Lindy. And we have some social media questions coming in with the hashtag #AskNASA. Another one for you, Lindy. Why is this metallic asteroid named Psyche? This is from Carmiles on X.
This asteroid was discovered in 1852 by Annibale de Gasparis at the Naples Observatory, and it was only the 16th asteroid discovered, and that's why it's numbered 16 Psyche. And that was a time when all solar system bodies were still being named after gods and goddesses, and so de Gasparis chose Psyche for this asteroid, and we named the mission Psyche so that no one would forget what we were doing.
Great answer. Now, Don on YouTube asks, do you think there'll be a chance of a lander mission to Psyche after this orbiter mission, assuming something intriguing is discovered? Maybe Laurie Glaze.
Take that one, Lindy.
I think it's you, Laurie. That one's for you.
I can take that one, Raquel. It's a really interesting idea. I think it is going to be fascinating to see what we find at Psyche, and we really don't know what that's going to be. And of course, there have been examples in planetary science history where we have gone and done our initial kind of exploration to understand what a body is, and then followed up with something that lands. There are so many objects in the solar system that are worthy of landing on, and who knows? Psyche may be one of those. We're gonna find out when we get there.
See what the future holds. Thank you so much, Laurie. And we have another social media question coming in. Borg750 on YouTube asks, given the project began in 2011, what will the resolution of the primary optical camera be? Henry, do you want to take that one, clarify this one?
The resolution, boy, that may almost be a better one for Lindy. I think it depends on the altitude that we're taking pictures of, but we'll be able to, resolve surface features, down, I think it's to 50 meters or so. Lindy, you could probably chime in on the final resolution.
Yeah, no, I think we're going to get down to a couple meters and maybe even better. And so we'll really be able to see what that surface looks like. If not at a micro scale, at least, you know, it'll feel a bit like we're walking around.
Great. We also have some questions on the phone lines coming in. We have Marcia Dunn with the Associated Press.
Yes. Lindy, I'm going to ask you to put your creative imagination cap back on. Do you think when you start seeing the pictures, would you anticipate some glitter, shiny surfaces, or all pretty much dull everywhere, maybe a mix? And what color? Silvery gray? Might there be other colors there if there are other metals? And a more basic question, during the 100-day checkout before the thrusters are fired to go to Psyche, where will the spacecraft be? Thanks.
Yeah, well, Henry can talk more about where the spacecraft will be. It'll be transiting away from the Earth towards Psyche at high speed. And so in terms of what the surface is going to look like, you can imagine I've had many dreams over the last 12 years of what it might look like. And I would love for it to look like a shiny, polished, what's called a palisite meteorite with the shiny silver metal and the beautiful gold and green jewel-like silicate minerals in between, but it's not going to look like that because no one's gone to Psyche, cut it open, and polished it. It's been hanging out in space, getting solar wind hitting it for a really, really long time. So the surfaces are not likely to be shiny, and there's really only going to be one metal on the surface. When people talk about there being metals other than iron and nickel, they're dissolved in the iron and nickel. You can't see them. And so we're not expecting a shiny surface. I do have a hope that in the distant past, the baby Psyche, the proto-Psyche, the parent of Psyche maybe had active sulfur volcanoes on it. And I could tell you at length why that would be scientifically, but it is not worth the time. But we think that could have happened, in which case there could be sort of a dull goldish green on a part of the surface. We do have a multispectral imager, so we'll get some idea of colors. Probably everything I just told you is going to be wrong when we get there.
Thank you, Lindy, for those answers. And we also have Stephen Clark with Ars Technica on the line.
Thank you. I think mine's for Lindy as well. Do we know anything about where Psyche formed, or the protoplanet that became Psyche formed? Did it start its journey in the asteroid belt near its current orbit, or did it migrate in or out? Thanks.
Yeah, we don't know for sure, and we may never know for sure. It's likely that a lot of those early planetesimals, the little bit baby planets, formed closer to the sun and were thrown outward. It's much easier, if you throw things inward, they tend to end up in the sun. So it's a little hard to get the throw inward just right. Probably not a lot of there's probably parts of the asteroid belt that formed where they are and other parts that were implanted, both from inward and from outward. And so that's a way of saying my bet is that it formed closer to the sun. We may never know, and it could have formed in place or even further out. So not very satisfying answer, but that kind of sleuthing is super hard to do.
Thank you, Lindy. We also have another follow-up question coming in from Emily Ladaguala from Sky and Telescope.
Hi, yes, I just wanted to follow up with a question about when you expect to get, I guess not better than Hubble, because we're not going to get the same as we got for Vesta, but how many days prior to orbit insertion do you expect to be able to really begin to see surface features?
Henry, do you remember what our Discovery approach image schedule is?
I don't recall the details of it, right? But the actual approach will begin about 100 days prior to our going into the first orbit.
Thank you. We are now moving on to some social media questions with one for you, AB. Greg on YouTube asks, what is the bandwidth difference of DSOC compared to the current DSN, and how far will it still work?
Thank you for that question. So the typical DSN, like Ka-band, is about 25 gigahertz, whereas the optical communications we're doing is about 280 terahertz. So it's orders of magnitude higher in bandwidth. And we are able to communicate from about the Mars farthest distance, which is about 2.7 AU roughly.
Great, thank you, Abi. So Alfred Simmons on X asks, how can the core of a planet even form? Lindy, would you like to take this one?
Yeah, this is one of us planetary scientists, one of our favorite processes in the solar system. Lori and Laurie are smiling. The original material around our solar system, which we know from meteorites, had very finely mixed, intimately mixed bits of metal and rock. And we have evidence, and this is just shocking science, which I still can't even believe. We have very good evidence that there was a really hot radioisotope, aluminum-26, active in the early solar system that melted that material when it got into big enough clumps. So you make a clump the size of Australia, and it melts on the inside from this radiogenic heating. And then the metal, which is twice as dense as the rock, the metal sinks to the middle and leaves the rock floating on the outside. So that's how these metal cores formed. And it's incredible sleuth work that we've been able to figure that out. It's really, I think it's super exciting to think about.
It's all fascinating. Thank you, Lindy. We have another call on the line, Alexander Whitsey from Nature magazine.
Hi, thanks. This is actually a follow-up for Lindy on what you were just talking about. Can you talk a little bit about implications for exoplanet studies? Like, could things like Psyche form around other stars? And if so, how would they be comparable to what we might be seeing from Psyche?
Yeah. Hey, Alex. Nice to hear your voice. Yes, there is already evidence for exoplanets that seem to be very, very dense and probably made largely of metal and maybe even have metal surfaces. A suspicion would be that those exoplanets were not the cores of other planets that got broken apart because they're really huge, but instead material that was formed in very hot or very oxygen-poor environments so that the iron atoms formed metal instead of iron oxide. So we think of iron oxide as typically what the state that iron is in rocks. But for Psyche and for these exoplanets, the iron is in the form of metal. So probably that is an environmental planet-forming circumstance, a little different than Psyche's, but it's a whole new class of bodies to study, and there are a lot of scientists very excited about it.
Great, thank you, Lindy. We also have lots of social media questions and comments coming in. Just like Fred Hernandez on X says he is excited thinking about how many different minerals we will find. And then we have Flavia on YouTube who asks, how long will it take to communicate with the spacecraft and back once it arrives at Psyche?
That's Henry.
Henry?
Yeah, the communications will, vary from tens of minutes to 20 minutes or so, depending on where the orbital alignment of the various bodies. We're orbiting the sun at different rates, and so the distance from Earth to Psyche will change throughout the mission.
Great, thank you. Up next, we have a follow-up call with Marcia Smith with spacepolicyonline.com.
Thanks so much for letting me ask a second question. This one is to Abi. Could you again go over what you're saying about using a beam from Palomar Observatory as your target? And is this just as part of the demonstration, or do you anticipate that in the future, when optical comm becomes more commonplace, that you will always need some laser beam emanating from Earth to guide the signal back?
Thank you for the question. Yeah, so the DSOC architecture is what we call it, is a beacon-assisted architecture where it relies on a laser being transmitted from Earth, which serves as a pointing reference. Now, but that's not the only architecture. One can imagine an architecture where you didn't use a beacon assist, or you used a celestial beacon. And especially when you go out to farther reaches of the solar system, the celestial beacons, like even the Earth, could act more like a point source. So in that case, you may not need a laser, and it's also going to be more difficult to transmit a laser that far. But to Mars distances, a laser seems like a reliable and reasonable choice. So if there are future Mars optical comm missions, they will probably be beacon-assisted architectures.
Great, thank you, Abi. We have a couple of social media questions. We have Total Arc on YouTube who asks, is this data public information? Lindy?
Yeah, I would love to have Laurie Glaze address this also, but absolutely, space exploration is for everyone. So Laurie, tell us all about that.
Yeah, so it is NASA policy that everything that we do in space science is made publicly available to anyone who wants to have access. And so within planetary science, we actually have an archive system called the Planetary Data System, and all of the Psyche data will be made available through that archive, just like all of our data for all of our missions is made available through that resource. And that we have similar archives for all the other divisions. I've heard Lindy say that the image data are going to be made available very quickly. We do that in several of our missions, trying to make those image data available to the public as quickly as possible, so everyone gets to experience the excitement of discovery all at the same time.
Thank you, Lindy and Laurie. We have a fun question coming in from Bill Thon on YouTube. Asks, please tell me that there's a theme for naming features on the surface that will be metal bands and artists. But in all seriousness, what surface features will be named, if any, on the asteroid?
We will be naming surface features, and this is totally adjudicated by the International Astronomical Union, the IAU. And we have been talking with them, and they're ready to have serious conversations with us once Psyche is up and cruising. Because we like to do things all together as a team, in fact, I asked the team a few years ago to give me their votes on categories for naming. And a number of people did want heavy metal bands, that's for sure. That was one of the things that came up. But there are a lot of other options, and that will be decided in the next couple of years, what categories.
That sounds really exciting, Lindy. And we have another social media question coming in from Stephen on Facebook, who wants to know, will humans ever visit an asteroid or comet? Laurie, Lindy, would either one of you like to take that one?
Laurie or Laurie? Yeah.
Yeah, I'll take that. I think we, as humans, we love to explore. We love to do things that have never been done before. I know I'm not supposed to speculate, but I think at some point, I hope that humans can touch all types of different bodies in our solar system. I think it would be fantastic. I'm not sure when that will be, but it would be so cool.
Well, that is a great note to end on. Thank you so much. That is all the time we have for questions today. And thank you to all our speakers. To stay updated on the Psyche mission, follow NASA JPL and NASA Solar System on Facebook, X, and Instagram. To learn more about Psyche and stay updated on its October 5th launch, visit nasa.gov/Psyche. Thanks again for watching.